Hello everybody, welcome back. Today we are continuing to study the application of machine learning to battery lifetime prediction. In particularly, we are going to focus on feature engineering, which definitely is my favorite topic in data efficient machine learning. We are going to go through why feature engineering is important, how to extract features, and how to select features. Let's dive in. So we were talking about we can build a data-driven workflow for battery lifetime prediction. Indeed, we collect our initial data from battery cycling or battery aging tests. We build our machine learning models, and then we apply the results from our predictive models to different industry applications of batteries. So why we need this additional step called feature engineering in between the data collection and the modeling? So typically, we have feature engineering where we actually transform the raw data into a format that is most suitable as the input to our model. We do it for multiple reasons. One of the key advantages is that this is a chance for us to select the features that are most informative and relevant, which improves the accuracy of our predictive model. As we reduce the number of features as input, we also reduce the complexity of the modeling process. We also take this chance where we can start to build physics-based features, which enhance the interpretability of our data-driven method. Also, data like efficient machine learning kind of indicated like why we use feature engineering, because by selecting the features instead of taking the raw data set, this method is very powerful when we have a small data set. Let's dive a little bit into why small data set is very applicable in our case. So battery lifetime data is limited. When we charge and discharge a battery, we get data looking like this. We have the current and the voltage, and the data has been recorded as a function of time. So this forms like a one cycle of battery lifetime data. So typically in experiment or like a real-time cycle, we can say, well, we can take around 2,000 data points. At this point, you will be thinking, wait a moment, but we are actually doing a battery cycling test for over the years until we get enough information about when the battery starts to degrade. That's true. When we are starting to build a training data set, we continue to cycle our batteries for many cycles until the degradation started to be obvious, and we can validate our models. So let's say we have our batteries cycles to 500 cycles. Right there, immediately, we realize, wow, that's immediately we have 1 million data points to build our models. You may ask, wait a minute, that's not a case where data is limited. Well, remember, while we have so many individual data points, all of them are kind of taken from a segment of a battery's whole lifetime. In other words, all of this data, time series data with rich information, were taken from one battery. For us to really build a comprehensive model to predict batteries, a state of health over a range of different conditions, we need to collect many batteries with a diverse lifespan. And typically, with our real life constraints and budgets, it's common we have hundreds or in the order of hundreds of batteries being tested in parallel. So in this case, we are in a situation where the number of features, or the number of the dimensions of our input data from one battery is much larger than the number of independent battery cells. So here we are in a situation in machine learning, you can refer to as curse of dimensionality. So in this high dimensional input feature space, our data is very sparse. So this can make the learning of the patterns harder. We also encounter challenges such as the overfitting and also the poor generalization of our models. In addition, like a lot of the features like also means like the slower computation. So we may have a challenge in like managing our computational resources. So what do we do then? So here is a chance for us to start to reduce the number of features in our model through the careful feature engineering. Let's take a battery early lifetime prediction as a case study. So in this paper presented on the slides, the researchers from Stanford, MIT, and the Toyota Research Institute were tackling this challenge of building a data-driven prediction framework so that we can forecast the battery cycle life. In this case, it is defined as like when the battery reaches the 80% of the state of health values. And we want to like make a model to predict the cycle life of batteries before the degradation in capacity measurement is very obvious. So in other words, the researchers cycled through 124 commercial lithium-ion batteries, and by changing their like fast charging protocols, that leads to a diverse cycle life of batteries from 150 cycles to over 2,000 cycles. So in this case, the problem formulation is that we are trying to use the information from the first 100 cycles of the battery cycling data to predict the cycle life in the future. So this is like a really good example where we can evaluate the power of feature engineering. So in this case study, the researchers first tried to explore like how like the early features can impact the model performance. So for example, we can extract the discharge capacity measured at cycle 2 or at cycle 100. We can also explore the slope in a way the change of discharge capacity between two different early cycles. But as you see from the values of like the coefficient of correlation, where we compare how these features being selected are correlated to the final prediction target, which in this case, it is the cycle life. So we can see from the numbers, for example, minus 0.061 is not very high. So in other words, these early features are not very informative when it comes to using it to predict the cycle life. What do we do next? So here is like a chance for us to apply domain knowledge of lithium-ion batteries. In other words, our understanding of like the battery degradation mechanisms and how different degradation mechanisms would be reflected on like the battery cycling data to like explore new features. And guess what? By working with like battery experts, a magic feature was discovered. So in this case, as you see like on the slides, the researchers found out if we have the function where like in this case like we can plot like the voltage as a function of discharge capacity for each individual cycle, and then like we can take this relation between the discharge capacity and voltage for each cycle and their differences between the cycles, and we take the variance of this data, and this creates like a new feature, like as shown here, the variance of the capacity differences as a function of voltage. You can see this feature is highly predictive to the cycle life. So indeed, so in this study, the researchers found out like even with this single feature, we were able to build a pretty accurate predictive model, like where we use like the information from the first 100 cycle only to predict the final like lifetime of a battery. We can leverage our domain knowledge of how a battery degrades or just how a battery works to help us to extract the features. Let's name a few examples. If we consider just a single cycle, we can extract the electrochemical features from a cycling test. Here, we have the voltage as a function of capacity in one cycle of battery test. We have our charging curve, and then we have our discharge curve. From this information, we can calculate our Coulombic efficiency, or in short CE, which is the ratio between the charge during the discharge period over the charge over the charging period. This capacity ratio would help us to have an idea of how the charges are transferred throughout the full cycle of a battery test. Similarly, a lot of times we are interested in how a feature changes from one cycle to another, because this encodes degradation information. So here, for example, we have the capacity changes as a function of cycle number, or in other words, as a function of time. So over the time, we see the capacity decays because battery degrades, and we can extract two specific cycles, and then we can calculate the slope of such capacity changes. And different slopes gives the idea of the rate of the degradation we see in the battery. If you talk to battery experts, you may be told that in the field of battery research, a lot of times people are interested in differential features. So here we see the dq over dV as function of voltage. So for a specific battery, you may see a curve look like this. And of course, for different cycles, if you compare a new battery with the degraded batteries, you'll see the curves look differently. With that in mind, we can extract features such as the peak position from this differential curve. And this would help us to have insight of the battery degradation mechanisms behind the observations of the capacity decays. And we are talking about a time series data when we are talking about a battery cycling test. And of course, we can also extract time domain features. For example, during a battery charging exercise, or during the protocol design period, we can have the voltage changes as a function of time. And here, during this charging period, we can say, let's take the time feature, which is the time when the battery voltage stays constant as a feature, and we can use this information to help us build machine learning models to predict the battery degradation. So with so many features we extracted, we are ready to build a feature database. So in this paper, cited on the slides, the researchers were able to extract over 300 individual features, and all this information can be used to build the predictive models. And of course, at this stage, maybe it's the case that not all the features are needed to build our model, and the feature selection process will take place. We start to reduce the features that are not that informative, and there may be a diminishing return of how much additional accuracy we get from our models by adding individual features. And then this is where the feature selection would take place from here. So we discussed so many features can be extracted from the battery cycling data. One more thing I want to share is that battery testing occurs at different stages of a battery's life. So for example, before a new battery goes to the market, formation process is the last step of battery manufacturing. So we are talking about a new battery just get assembled into devices, and formation is the first time a current passing through the battery. So we can take this information to help us to predict the future battery performance, and this allows us to do quality control and making sure only high quality batteries are going through to the market and leaving the factory stores. So how do we do that? So we can take the curve of a formation process. Typically, this protocol of formation is determined by the battery manufacturing. Then we have a specific set of protocols we apply to the batteries being made. So if we take the voltage as a function of time, we may see a formation curve look for example, something like this. And of course, when we apply this protocol to different new batteries, they may behave slightly differently, and we can take the information to help us make predictions of the future battery health. We can also take the information from diagnostic tests. This is typically conducted to help us to examine if there's anything wrong with our battery at different stages of battery's lifetime. For example, we can perform a hybrid pulse power characterization test. And in this test, we'll pass a high current pulse to our batteries and see what's the dynamic response of the batteries. And of course, we may have a protocol of the test look something like this. So we have the voltage goes up, and then we apply pulse at a different state of charge of the battery, and you can see it's the pattern in a diagnostic test looks quite different from the formation process data. And this obviously gives us different information about battery's performance and the underlying mechanisms of how the battery is working. Of course, just what we've been discussing, typically in a laboratory environment, we can perform controlled cycling tests to test their aging behavior. And you may find, if we come to draw, again, the voltage and time curve, you may say as function of time, we apply some voltage, and then they form regular charge and discharge cycles. And bear in mind, in the laboratory, it is more controlled, but we can also direct taking the data from a drive cycle. So where we have how the batteries behave in electric vehicles, and you can imagine typically the data here, in a drive cycle, is much more irregular. So you may have the battery going through a range of different voltage series, and there may be some regenerative braking going on, also changes the patterns, and all these different patterns of the battery testing or the battery usage history are there for us to extract informative features from. So we talked about different methods to extract features and different tests we can extract features from. Let's now also talk about some of the common pitfalls of performing feature engineering. Let's say this is battery testing protocols we use to collect the training data set for us to predict the battery's future state of health. We have our voltage data, we have our current data for one cycle. And let's say in our training data set, we have over 100 different batteries, and all of them has been tested with the same discharging protocols. But they have a diverse set of battery lifetime because they've been charged differently. So that means if we are talking about another set of the batteries, they'll be charged, say, in a slightly different way, and some of them may be charged in a very different way. So if our goal is to predict how different protocols are leading to different batteries state of health, then we can certainly take the features from the charging part of the tests. So in a way, we are having our models to learn the importance of the protocol to protocol difference. But maybe our goal is actually to study how one cell behaves differently from another cell, no matter whether they have been going through the same or different charging cycles. In this case, if our goal is to follow the cell-to-cell variation, then if our model has been built only from the features extracted during charging, then our model may be actually learning the protocol-to-protocol differences rather than learning the cell-to-cell differences. So in this case, taking the features from the discharge curves seems to make more sense. So conceptually wise, we are talking about a challenge, which is called data leakage. In a way, we don't want to have our model which is built actually to learn like the protocol to protocol difference, and we assumed it's been learning the cell to cell differences, and then if during the training it has like a high accuracy, and then we want to generalize it, it may not perform like as well. So this is kind of like important point about the feature engineering. It's like we need to understand what our models are learning from the feature we selected. So some of the features are based on the induced variability of our training data set, and some of the features can be extracted from the intrinsic variability of individual battery cells we've been testing throughout like the entire process. As we discuss like the choosing the right class of features, let's also think a little bit about like a broader context of feature generation. So fundamentally, we've been trying to extract information from the time series data of battery tests. And like we are aiming to reduce the dimensionality of the data. We are aiming to select the most informative or like most relevant features as input for our model. And this task, like instead of extracting the features by hand, we can also use machine learning to help us with this task. So in this lecture so far, we've been focusing more on the physics-based feature extraction. In other sense, like we are leveraging our domain knowledge of how battery works to help us very like efficiently and also with high interpretability to extract the meaningful features. We can also automate this process by just extracting the statistical features across our time series data. For example, we can extract the rolling statistics of the means, the maxima, the minima, and the variance across all the individual like cycles of the data available. We can also build like machine learning models to learn which features are important, and to like to learn like the features like not only like, just like what we see here. We can also have everything like to be on the latent space and use that as the input to our models. No matter what methods you choose to use, one thing to remember, the effective feature design is really kind of a balance between the efficiency and the information you get and the interpretability of the model. If you choose like a more physics-based model, physics-based features, and then like you are able to like interpret how like the physical meaning of the features kind of infer to how like the mechanisms of degradation behind like the observations of their degradation. So in other words, like this would allow us to consider to achieve the goal of our prediction, what are the set of input we would want our model to use. With that, thank you very much for listening, and see you next time.